Okay, now we did this as a class exercise. Our situation, for anybody that's watching this and isn't aware of the situation, we have a beam rotating in a circle. It's got a length of 60 centimeters, so its radius is 30 centimeters. And it's moving in this circle, and there's a penny resting on a magnet that's attached to the beam, a kind of smooth magnet. And we gave this thing a spin in class just to demonstrate what happens. And turns out the penny flew off of this thing and landed in a cup. The cup is still there. Okay, the system is still there. We haven't touched it because we're going to cover it in gold and make a shrine out of it. Because this is obviously a miracle because it defies all the laws of physics. It could not have happened, but we have several witnesses. Okay, and these are credible, most of them are credible witnesses. Some of them are shaky. No, we have a lot of people that saw this happen. I didn't see it. So hey, it went in the cup, and I looked, and there it was in the cup. It's the only penny I own, so I know that was it. Okay. Okay. Well, anyhow, that's a fascinating system. Okay. Okay. So what we did is we just broke into groups to discuss this, and people did a great job in this. I think better than anybody, or than most of you at least, would be likely to get on your own. Okay, because we got good ideas right from the very start. In the first discussion, back up. I analyzed this. Okay. Yeah, I was awake in the middle of the night. I needed something to put me to sleep, and I analyzed it. Now, I came up with a polynomial that looks very much like this. Okay. And the polynomial is a fourth degree because you got to square a lot of stuff. And one of the things you got to square is like a square root of 1 minus sine squared, or 1 minus sine squared in this case. And you understand how that comes up when you do any kind of circular trigonometry. And it turns out that this fancy Greek signal, I didn't want to use X symbol. I didn't want to use X because you can confuse that with X coordinates and stuff like that. So I just used the fancy symbol. And then I assumed, okay, let's just say, I know it happens somewhere around 45 degrees. Okay, it's 45 degrees. Then the sine of this angle here would be negative square root of 2 over 2, about negative 0.71, or just negative 0.7. Okay. And the cosine would be a positive 0.7. So this point would be the point on the rim of the circle when the position vector is at this 315 degree angle. I did that and I just plugged in because ain't no way I'm going to solve that equation. I don't think ain't no way anybody's going to solve it without just doing numerical approximations. Okay. I don't think it factors into two quadratics. Matter of fact, because the sign changes, I think there's one linear factor, at least. Yeah, you can go back to pre-calculus, what you learned about polynomials. You can apply that if you were to end up with one of these. I'm not going to have you do that, so don't panic. But we have this polynomial, so using the 45 degree, 315 degree approximation, I got 3,400 minus 2,700 equals 0. Okay. So I realized, okay, well, epsilon, or that's not epsilon, whatever this symbol is, if the sine of theta is negative 0.8, then this number is going to reduce. This number is fixed. It's not going to change. It's the sine of theta. And I got something that was within 100 of this. So I said, yeah, that angle's got to be pretty close to the inverse sine of 0.8. Okay. And that gives me like a 37 degree angle. So we conclude this is 307 degrees. At 0.8 was very convenient. It's very convenient because we know what the sine and cosine of 37 degrees are, like 0.6 and 0.8. Okay. And the 53 degrees you have here would be 0.8, 0.6, so the sine equal to 0.8 comes from. Well, all that's just background. So after that analysis, I think it has to be pretty close to 370 degrees. So 370 degrees, that's right. How fast does this thing have to be traveling to get that color? Or to get that point? Well, we know that the beam it's rotating, it's 30 degrees above the tabletop, the cup is sitting on the tabletop. So we know that the penny falls 30 degrees, 30 centimeters. And that was the first answer I got when I came in and just picked a number out of a hat and asked somebody to tell them what they got. Well, we're working on finding the time of fall, because once we have the time of fall, we can figure out this distance, etc. Okay. And figure out the speed. And that's exactly right. That's how you get beam on. Okay. So again, you can determine this position based on the idea that the angle is 370 degrees. You can figure out this R vector, figure out what this point is. Then you can use the Pythagorean theorem to find the distance here to here in the XY plane. Okay. Now this point is 30 centimeters below this point, so it takes about a quarter second to fall. So it goes from here to here in about a quarter second. Okay. So from the projectile motion, first of all, the angle and everything, you determine the coordinates of this point. And then you analyze the projectile motion from here to here and give you speed. And the velocity. Your velocity is just going to be the vector change in position. So let's just call this point P. We call this point Q. So here's the vector PQ. Well, actually, be here. And that's as reasonably tangent as this thing goes. Okay, so here's your vector PQ. You got that. Go this point, got the vector. How do you get this? You apply PQ by delta T. Okay, PQ is something like (40I plus 30J in units of centimeters). I stressed you want to have the units there. So you make sure your calculations are dimensionally consistent. Okay, that's what you expect. Well, when you divide this by your delta T, which is a quarter second, you're going to get something like 160I plus 30J centimeters per second. That's like 30, it's 120. Okay. Well, actually, that's kind of a 3, 4, 5 triangle, isn't it? So that means it's moving at about 200 centimeters per second, which is what somebody got just a minute ago. 216, I think, based on the numbers I gave. And I got around 200 when I did it. Okay. So I'm glad to know that I was halfway right. And that's your whole purpose, to confirm my thinking. Okay. Seriously, now, if you're in a research project later on in your engineering career, you know, in junior, senior year, we have a lot of research projects. A lot of times, a research project is really trying to find something out that nobody knows. Something your research advisor, faculty advisor, or maybe good graduate student advisor, knows that they could figure out, but they're going to let you figure it out. Okay. And maybe they do a ballpark approximation, and then you give them the number, and it's close to agreement, so they feel good and you feel good. So everybody's happy. All right, well, just a little digression. Anyhow, you see that we can pretty quickly get these things if we put things together. Just want to try to understand that. And somebody also was relating this projectile motion and worrying about whether things were in a plane and all that stuff, and that's good. You haven't had multivariable calculus, and you get the multivariable calculus, it'd be a lot easier to think about that. But yeah, the thing is describing a parabola in some vertical plane. Okay. Just like you shoot a basketball, if you're tall enough, you're shooting a basketball downward to the rim. Okay. most of us are shooting upward. And that whole projectile problem was one of the homework problems. Okay, so it's good to relate that homework problem to this. Okay, then get omega naught and the initial centripetal acceleration. Now we've got omega naught. Okay, from the fact that this thing, point the rim is moving at 200 centimeters per second roughly, the radius of 30 centimeters, tells us that it's somewhat between 6 and 7 radians per second. Okay, so you know the P naught and R gives omega naught. If you're unclear on that, many of you might be, ponder it. There's a formula for it, but think about why the formula works. Go back to what I said about radians. A radian of angle implies a radius of arc on the circle, the distance along the arc that's equal to the radius. So all the way around the circle, you got 2 pi times the radius is your displacement, which means you got 2 pi radians. All right. Well, you put all that together, P naught and R then go together to give you the omega naught. That's actually fine. If you know 2 of these, know you can find the third. Just by direct reasoning, and there are formulas, but formulas are hard to remember. They're easy to confuse because everything looks the same. You go blind. I'm pretty good at memorizing formulas. I gave up on memorizing which formula is which. I don't need that. I know what a radian is. Duh. Okay. And hopefully you get to that point. A few people are at it. Right now, people are still a little confused about radians. I was really like, and I think most people around me were, and we were pretty good. Okay. Centripetal acceleration. How do you get centripetal acceleration? Well, we talked about it last time. Take this vector and then a vector a little bit later, take the difference of the 2 vectors and divide by the time interval, and you get the acceleration. Okay. Velocity vectors. And you got 2 formulas. They're worth remembering, but you always want to be able, if you really want to understand this, to own it and to derive it. Okay. B squared over R is the easiest to remember. Omega squared R is fairly easy to relate to this if you understand radians. But if you don't, stick with B squared over R because that's going to be typically the easier one to remember and apply. But you know, do your best to understand both of these formulas. So what's B squared over R? Well, you figured out that Z was around 200 centimeters per second. R is 30 centimeters. Square 200, you get 40,000. Okay, divide that by 30, you get about 1,300. So you get centripetal acceleration about 1,300 centimeters per second squared. Now I'm going to ask you to fill in those blanks, work that out. Yeah, kind of write this off. Okay. So what's wrong with that? That exceeds the acceleration of gravity. There aren't many things that have so much frictional coefficient. And there's actually nothing that has a frictional coefficient that allows the frictional force to be greater than the force that's pushing the 2 surfaces together. Now, we'll talk about that. I've come up with a couple of chapters, so we don't worry too much about that. Just it's impossible that the frictional that you would get this centripetal acceleration from frictional force between the penny and the smooth magnet surface. We actually measured that. You know, we put the thing on an angle and we found out that you have an angle of around 30 degrees, basically, before the penny started to slide. Okay. Now, this Well, if the thing was vertical, the penny would clearly fall off. There would be no force pushing the penny into the magnet, and there'd be no friction. Okay, that would correspond to coefficient of friction of 1, or a frictional force equal to the gravitational force. Well, to hold it on there, the frictional force would have to be equal to the gravitational force. But clearly the frictional force is 0. Not sure that'll make sense. All I'm going to say is the centrifugal acceleration here can't exceed that of gravity, the force of gravity on the penny. Okay. And since the acceleration that you get here for centrifugal acceleration is greater than g, g would be 980 centimeters per second squared. 9.8 meters per second squared, right? 9.8 meters is 980 centimeters. There it is. Kind of throw that away. And we're getting 1300. So this is physically impossible. So you see what I mean? The gremlins must have been involved. I stopped short of quoting divine intervention. I don't think that would happen. Okay, just to give us something to think. Okay. So what's going on? We might spend the rest of this minute trying to figure it out. Okay. Okay, so talk about a lot of things related to this system. If you know 3, I'm just kind of giving you a synopsis of the main things you need to know. Okay. If you know 3 of these 5 things, then you can find all 5. We've been over that, so make sure you understand what I'm saying. This is linear motion. If you know I got V naught X, VF X, etc. through delta X. You have V naught Y, VF Y, all the way through delta Y. And you got an AY and a delta T. Well, I guess the small AX, AY, and delta T. I'm going to put delta T here because it applies both. Okay, so you don't have a separate delta T for the vertical motion and horizontal motion. Okay, so now if you know any 3 of these, okay, or any 2, well, okay, any 3 implies all, and any 3 includes delta T. Okay, here. Any 3 implies all, including delta T. So if you know enough to find delta T over here from these 3 of these 4 quantities, then you know delta T over here, so that's 1. An ideal projectile, you know the acceleration is 0. Acceleration 0 in the ideal case. Acceleration y. In the ideal case, acceleration here is g downward, wherever you're, whichever direction you choose for positive y direction, g is going to be in the direction opposite. G is going to be down. So g would be negative if your y-axis points up. It would be positive if your y-axis points down. And you could use either. Okay. Now there are other cases, but you automatically have this and this. So now you only need 2 of these to get your delta T. Or if you have to know your delta T, you only need 1 of these to get all of them. You always know AX. Okay. So you don't need much more. So you just, there's your situation. Okay, now there are a couple of tougher situations that I don't think I've seen in the problems, and I love them. But we'll talk about it a little. So after you, now quickly. Need you to submit everything that's been due. Okay, and I've been getting the piecemeal, which makes it real hard to organize the printing, so I haven't gotten it. Okay, so get me everything by like Friday. And sorry,
Including chapter 4.
by whatever's due in chapter 4.